Dear students, in the series of current electricity, the last class was so very important because the concept taught in that class, if you master, questions in the coming section will become very, very easy. We ended that session with this problem on the board where there is a network of resistors, okay, 20 volt, 10 volt, 6 volt, center point. I wanted you to calculate potential at the center here. Now basic idea, these come from practice, okay, that this is a higher potential, this is the lowest potential here, fine. So a current will flow from 20 volt to the junction here, call this current as I1. Another current will flow from 10 volt to the sender, call this current as I2, and together these will join and flow as I3 towards the least potential point. That's the way the current will flow from higher to the lowest one. Okay. Now let us consider potential at this point as V, which you need to calculate. Now I can say that the current I1 plus current I2 gives you the current I3, and I can use Ohm's law to calculate current here. We studied that current is nothing but potential difference divided by resistance. So 20 being higher potential, 20 minus V by 5 plus I2 should be 10 minus V by 5 equal to, here current flow from the junction to that 6. So V is higher than 6. So the difference must be V minus 6 divided by same 5 ohm. Is easy because the denominator is all same. So cancel them out. So you get 20 minus V plus 10 minus V equal to V minus 6. Take 6 to this side. So 20 plus 10 plus 6 equal to minus V that side will get a 3V. This 36, 3V equal to 36. So V must be equal to 12 volt. So the sender point will have a potential 12 volt. As we predicted, this potential is lower than 20, but this is greater than 10, so there may be some correction in the direction of the current. Okay, that means the current in the 5 ohm resistor here is not flowing in the proper direction as we expected, it's in a different direction. Okay, now the potential at the sender is given as 12 volt, but now there is a problem that we assumed that this is at a higher potential than that. But now it turned out to be that this is lower potential than that one. So the direction of the current that we selected is not correct. Okay. Then what should be the actual direction of the current? Let us see this. Let us see this. So this is at 12 volt. So 20 and 12. So current I1 should be flowing like this. I1. Fine. What about the current here? This is 12 and this is 10. So this current should be flowing I2, and here it should be flowing from 12 to 6. That should be equal to I3. So this assumption is not correct. The assumption is not correct. In reality, I1 is equal to I2 plus I3. And then you can check I1. I1 is 20 minus 12. 20 minus 12 by 5 equal to I2. I2 should be taken as 12 minus 10 by 5, and I3 should be equal to 12 minus 6 divided by 5. And I think this is also correct. All 5 cancel. 20 minus 12 equal to 8 equal to 12 minus 10 equal to 2, that is equal to 6. So you are correct. There is no issue in the calculated value, but the assumption was not correct. Okay, here one of this current I2 became negative current. That means we assumed that it was flowing in that direction, but actually it flows from the opposite direction. But don't worry about that. However you assume, your answer is going to be correct. Your answer will correct you. Okay, so this is the answer. So 12 volt is the potential at that center point. Fine. Okay. Now what? Now see, there is another circuit like this. Okay, this is a point A, B, C, D, E, and there is a current showing 2, and you can calculate potential at each point. What is potential at B, C, D, E, etc. Okay, and I can tell you, see, the potential at A, let us take it as VA, and potential at E, take it as VB. Okay. So what happens? What is potential at B? Potential at B is equal to VA minus the voltage lost here is 4 volt. That is 4 volt. Similarly, potential at C equal to how much is lost here? 3 into 2, 6 volt. So that must be equal to V minus A minus lost here plus lost there. VA minus 4 plus 6. Similarly, what is potential at D equal to? Now you can see that at D there is some voltage loss. How much is that? 8 volt. So we can say that is VA minus 4 plus 6 plus 8. And what is potential at E? Potential at E equal to, I am sorry, I call this as B. That is not B. This should be E. Please correct it. And VE is nothing but VA minus lost here is 4 plus 6 plus 8, and here how much? 5 into 2, 10 volt is lost plus 10. So VE is equal to VA minus, V equal to VA minus 10 plus 10, 28, right? Am I right? 4 plus 6, 10, 18 plus 10, 28. So what is the total difference VA minus VE? What is VA minus VE from this one? VA minus VE equal to 28 volt. So you can calculate a total potential difference if you can apply this technique. So this type of question can also come in examination. It's there in your compendium. Go and work out similar questions. Pick them, work out. Okay. Next one end of a nichrome wire of length 12 and cross-sectional area A is attached to an end of another nichrome wire of length L and cross-sectional area 2A. If the free end of the larger wire is at an electric potential of 8 volt and the free end of the shorter wire is at an electric potential of 1 volt, the potential at the junction of the two wire is equal to. This is a combination of the concepts learned in the previous classes. There is a nichrome wire of length 12. There is a nichrome wire of length 12. Say this is length 12 and cross-sectional area A. It is attached to an end of another nichrome wire of length L and cross-sectional area 2A. So the next wire is a thick wire, but it is a shorter wire. It has got a length L, but the area of cross-section is 2A. If the free end of the longer wire, this longer wire, is kept at 8 volt and the free end of the shorter wire, this is a free end, this is kept at 1 volt. What is the potential at the junction here? Call it as V. Just use the previous method. But what's the difference? What is the resistance here? What should be the resistance here? R1 and R2. I can draw an equivalent circuit here. I can say this is R1, this is R2, this is at 1 volt, this is at 8 volt, R1 here and R2 here. Okay. To find R1 and R2, what we can do is this: R1 is nothing but rho into L by A can be applied. So what R can be, you can use R equal to rho into L by A equation. So what is R1? R1 is nothing but rho, there must be some value which is not given, rho into length is 2L divided by area is A. What is R2? R2 is what? This is the conductor R2, rho same material but length is L, area is but 2A. So R1 and R2 are related. Okay. Now substituting that value, I think you can easily calculate it. You can take, okay, leave it. You can do like that. So let me do that. What is this potential is V. So you understand that there is a current flowing like this. This current will flow through this wire, go through the junction and enter the second wire. These two currents will be the same. So we can say current in the first section should be equal to current in the second section. What is current in the first section? See that one, 8 minus V divided by R1. And that should be equal to V minus 1 divided by R2. Substitute 8 minus V by, what is R1? Rho into 2L by A equal to, this is V minus 1 by rho into L divided by 2A. This is it. Okay. Now you can cancel different terms. A here and here will get cancelled, rho cancels, L cancel. What you get is 8 minus V by 2 is equal to, here you get V minus 1 into 2. Okay. So this is nothing but 8 minus V equal to V minus 1 into 4. So you will get 8 here, minus 4 will come here, plus 4 equal to, V go over there and you will get 4V plus V, you will get a 5V, you can solve this. So this is the basic idea. We find out the potential difference, then we find the current, equate the current because these are the same wire, same current will flow, and the resistance of the first part, rho into 2L by A, second part rho into L by 2A. Then work out like this one, you will get 12 equal to 5, so you will get V equal to 12 by 5, which is nothing but 2.4 volt. Which option? Option A will be the correct answer. Fine. Okay, little complex but simple in concepts. Mathematically complex? Yeah, this is how we work it out, and the final answer is 2.4. Okay, this is a better diagram, graphical, than my diagram. Fine, junction. See the structure of the conductor? Okay. Now, if you can also try this question. What is the current I in the circuit? The current I here, current I. How to find this current I? Use the concepts learned. The cell has got 2 volt, so take this as 0 volt, this as 2 volt. So at this point, potential should be 2 volt. At this point, potential should be equal to 0. Fine. Now you can see current flows here like this. These two are actually series connection, 10th standard. We will be discussing series connection later, but this is the idea from the 10th standard. Okay, current flow like this and the current comes like this. So these two are in series. Now you can say this current can be called as I1, this current can be called as I2. So there is a current I coming in, and that is branching out as two currents I2 and I1. So we can say current I is equal to I1 plus I2, which is I1. What is I1? See, I1 is a current in 30 ohm. This point is at 2 volt, this point is at 0 volt. So the current is 2 minus 0 divided by 30 plus what is the potential here? It is 2 volt. What is the potential here? 0 volt. So the total potential difference is nothing but 2 minus 0. But what is the resistance here? 30 and 30 in series will give you 60. Okay. So this gives you 2 by 30 plus 2 by 60. You can calculate this. Okay. So that is 4 plus 2, 6 by 60. You will get it as 1 by 10 ampere. Later on, when we study parallel combination of resistors, you can simplify this, and in one step you can get them. If I look at this one, if I am to do this in my own way, I will say 60, 30 parallel give you 20, 2 by 20, 1 by 10 direct answer. Okay. So we will have to study analyzing problems in different approaches. Whichever is easy for you, you should follow that one. Alright. Okay, dear students, now we are in a very important topic in the lesson, which will be useful for many classes coming after this. It's called a cell. It's called a chemical cell. It's an electrochemical cell, not the cell in biology. It's an electrochemical cell, and you know it's a device which converts chemical energy into electrical energy. Fine. Every mobile phone carries cell like that. Cell has become important in our life. You studied about a nickel cadmium cell, all those things. Fine. Now what we need is an understanding about how we handle cells in our circuits. A cell is symbolized like this. positive terminal, negative terminal. Okay, terminal means, what is the meaning of terminal of a cell? This is a dry cell, normal cell, this is called dry cell. This is the positive terminal. It's the positive terminal and this is the negative terminal. All connections are made at the terminals. If you want to connect a bulb, you connect it here. Any device you connect across the terminals. If you have a set of cells, you call it as a battery. A battery is represented like this. Battery means a combination of cells. Basically, a cell has got an electrolyte, a chemical solution, sometimes purely liquid form, sometimes in a paste form. In dry cell, it's in a paste form. And there will be two electrodes, normally we call it as positive electrode and negative electrode. It will be marked positive electrode and negative electrode. And the connections. So, in this diagram, these are the terminals, here these are the terminals. This is terminal number 1, this is terminal number 2. The connections are done on the terminals. Electric current will flow in a cell. From the if you connect something here, suppose you connect a bulb here, suppose this is a bulb is connected like this, then electric current will flow from the positive terminal through the bulb, then back to the negative terminal and inside like this. It's a complete path. It will flow from here, then through the bulb, then like this. This is how it flows. Okay. Now, in this diagram, you can represent that using a connecting wire up to this point. Then the bulb is represented using this resistance and that runs up to this point. This is how the current flows. And inside the cell, this will flow through the electrolyte back to this point. So that's what I say, the direction of current is from positive terminal to the negative terminal outside and negative to positive inside. And I also told you that when current flows through outer circuit, it loses potential. When it goes through the cell, it gains potential. This is basically what we want. So hereafter, whenever I say terminals, remember these are the terminals of the cell. And I'll tell you, this is the external resistance. But inside the electrolyte, when current flows, there is opposition here. So there is resistance here also. So there are two resistances that you should see. There is resistance inside the cell and there is outside also. Outside one you can connect and disconnect, but inside one it's always there with the cell. So every cell has got some resistance inside. That's called internal resistance. Internal resistance. Okay, this internal resistance will definitely depend on the nature of the cell. It will depend on the nature of the two electrodes. It will depend on the electrolyte, its temperature and many other properties. Okay, so a chemical cell, the symbol positive terminal, negative terminal, a battery, the basic structure of a cell, electrolyte, current flows like this back through the cell like this. Okay. Now this is a cell connected to an external circuit. So this R is the external resistance, this is the cell. This P and N represents the terminals, positive terminal higher potential, negative terminal lower potential. Current flows in the outer circuit like this. Direction of current is outer circuit positive to negative, but inside it is negative to positive. Is that okay? Now, two important terms I have to teach you. See this thing. This is a cell not connected to anything. And this is a cell connected to some device, a bulb, some toys, anything. Some external resistance is given. This is called a cell in open circuit. Nothing is connected means open circuit. And here this is in a closed circuit. It's in a closed circuit. Here there is no current flowing, here there is a current flowing. Manasilayo. This is going to be very important later. One cell open circuit, second cell in a closed circuit. Terminals of the cell, these are the terminals, P and N are the terminals, P and N are the terminals. And you know, voltmeter is a device which can measure voltage or potential difference. Okay, more on that later. But now, assume that I am connecting a voltmeter here as well as there. This is the voltmeter connected to these 2 points. A voltmeter is connected to a cell in open circuit, and a voltmeter is connected to a cell in a closed circuit. Okay. Now, if it is the same, even if it is the same cell, okay, suppose this reads 10 volt, suppose this reads 10 volt, okay. This is something that you will study later, that the current taken by the voltmeter is negligible. Current taken by the voltmeter is negligible. So, same negligible current is taken here as well as here. But this cell is giving you an additional current. So, you can say current through the cell here can be taken 0, but current through the cell is not 0. So, this is a cell which is not delivering current, this is a cell which is delivering current. Okay. If it reads 10 volt, this will read less than 10 volt. Though it is the same cell, this will read 10, that will read less than 10 volt. This phenomena you must have experienced this even at your home. When you suddenly turn on a heavy machine like a motor, a pump, mixie, etc., look at the other lights. Suddenly you will always see there is a sudden dimness in the light everywhere. Whenever there is a heavy machine starting to work, there is a reduction in the brightness of the different bulbs, which will disappear in a moment. It's always like that. Whenever you take current from a cell, the voltage shows a reduction, a decrease. That's what we are going to study now. This voltage shown, where is it shown? Between the terminals here and here. Cell in open circuit. That means it is not delivering any current other than the very small current through the voltmeter. But this is providing current because it is in a closed circuit. Both the cases you are talking about the potential difference between the terminals. Potential difference between the terminals. Potential difference between terminals of a cell in open circuit, potential difference between the terminals of a cell in a closed circuit. Closed circuit means delivering current. This voltage measured is called EMF of the cell. This is called EMF, and this one is called simply V. This is called electromotive force. Electromotive force, and this is called terminal voltage. Terminal potential difference or terminal voltage. Electromotive force is not force. Understand that. It is not force. Important point. It is actually a voltage, a potential difference. It's work by charge. I am telling again, a cell in open circuit shows voltage between its terminal, that's called electromotive force. The same cell in a closed circuit delivering current shows a slightly less voltage, is called terminal potential difference. This is what we are going to study in the next 2 slides. Electromotive force, written as E or sometimes as epsilon. What is the concept of this one? Maximum electrical potential difference that a cell can create across its terminal is called EMF. Its conceptual answer. It is equal to the potential difference across the terminals of the cell when there is no current flowing. Definition. Work done by the cell in transferring a unit charge once around the circuit is called the EMF of the cell. Important point, it is not a force, it is work per unit charge, its unit is not a Newton, it is volt. For examination, you write this definition. For doing numerical problems, you study this, especially, see, you study cells are chemical cells. Chemical cells can produce a voltage which can calculate chemically, and that is what we say created by the cell. That is the maximum that the cell can give. Terminal potential difference. Electrical potential difference available across the terminals, same terminals, is called the terminal potential difference. It is equal to the potential difference across the terminals of the cell when there is a current flowing. Its SI unit is volt. Okay. Now, coming back to the circuit again after the definitions. Open circuit, the voltage is called EMF. Close the circuit, that voltage is called terminal voltage. So, which one will measure EMF, which will measure, or rather which will show EMF, which will show terminal voltage? This voltmeter will show EMF of the cell and this will show the terminal voltage. I think this idea is clear. More on this later, because a cell can be charging, a cell can be discharging. We will study about more details in the next class. Till then, bye, see you, thank you.